Hello, welcome back. This video covers section 9.3, which is logarithmic functions. Logarithmic functions and exponential functions are inverses of each other. We can convert between logarithmic and exponential forms. If x and b are positive real numbers, such that b does not equal 1, then y equals the log of x base b is called the logarithmic function with base b, where y equals the log of x base b is equivalent to b to the y is equal to x. This is also one of the first objectives that you'll do, is to be able to convert from exponential to log and from log to exponential. So for the first few, it says write each equation in exponential form. When we write in exponential form, remember the base is the smaller number here. So this is going to be 4. We call that the base. So 4 squared, so remember the exponent is on the other side of the equal sign, is equal to 16. It kind of makes like a circle. So 4 squared is equal to 16. For number 2, I have 5, which is my base, raised to the negative 1 power is equal to 0.2. And then for number 3, I have 8 to the 0 power equals 1. And then for number 4, I have 23 to the 0 power equals 1. All right, so now we're going to do the opposite, which is to take the exponential form and to now write it as a log. Okay, so let me scroll down a little bit. I have write each equation in logarithmic form. 2 to the 4th power is equal to 16. So this would be written as the log of 16 base 2 equals 4. So notice that the base is the one being raised to the power, and then it becomes the little number when you write it as a log. All right, number 6. The log of 3 base 27 equals 1/3. And number 7 would be the log of 16 base 1/4 equals -2. And you can always check it by doing the reverse. So for example, this would be 2 to the 4th power equals 16. This would be 27 to the 1/3 power equals 3. And then this is 1/4 to the -2 power is equal to 16. So you can always check it by rewriting it in the opposite form. And so hopefully that helps you. Sorry, I kind of ran into the problem there. Okay, so now let's talk about evaluating logarithmic expressions. And I want to point out that sometimes we can evaluate logarithmic expressions and get nice, neat numbers. Sometimes we absolutely have to use a calculator to do this. Okay, so I'm going to start this first one. It says evaluate the log of 144 base 12. What this also says is this expression basically means 12, which is our base, is raised to some power, results in 144. And we have to try to figure out what that power is. And that is what the log of 144 base 12 is going to be equivalent to. Okay, let me do it with this one. So this one would be very similar. It would be 64, which is my base, raised to some power is equal to 8. And then this last one over here would be 3 raised to some power is equal to 1/27. Okay, so now I'm going to go through and figure out what the exponent is. So 12 raised to some power equals 144. Well, I know that 12 squared is equal to 144. I know this is true. So that means that I could replace the log of 144 base 12 is basically it's equal to 2. Now for number 9, 64 raised to some power equals 8. The fact that 64 is larger, so the fact that the base is larger than this number means it has to be a fraction. And I know that 64 raised to the 1/2 power is equal to 8. And so this whole piece can get replaced with a 1/2. And you can use a calculator to help you to find these numbers as well. All right, and then this one, 3 raised to some power equals 1/27. Well, I know that this some power must be negative. I know it must be a negative for it to result in a fraction answer. And so I might play around with the numbers. But I know that 3 cubed is equal to 27. So 3 to the negative third power would be equal to 1 over 27. So this whole piece can get replaced with a negative 3. All right, now I'm going to introduce you to some key definitions. It says the common log we can write as y equals log of x base 10. And because it's base 10, it's so common because it occurs with earthquakes and with pH scales that we can leave the base blank and it's going to assume to be 10. All right, so if there is no base written, you can assume that it's 10. We have another special natural logarithmic function that says the base is e, which you've seen with PERT. Then we can write that as y equals the natural log of x. And log natural represents ln. Okay, now these are so special. So these are both so special that they're on most basic scientific calculators. So you might want to look on your calculator for the word log, and you also might want to look for the ln on your calculator as well, because you should have that on your calculator. All right, so we're going to evaluate some of these, and feel free to use your calculator at this point if you would like for these 4 problems. So you might pause the video and try your calculator and see what you get. Actually, really for the next several problems. All right, so these first few I could do without a calculator, but then below I would have to use a calculator. So I'm going to go ahead and do these without a calculator, but I want you to know you could use a calculator. So this basically says 10 raised to what power is equal to 100, which is 2. All right, and then this next one would say 10, remember, because that's the base, right? 10 raised to what power is equal to 0.0001, and that would be 10 raised to the 1, 2, 3, 4th power, but it would be negative since it's 0.0001. So that would be negative 4. And then this says e raised to what power is equal to e to the negative 3 power. Well, that's just negative 3. And then e raised to what power equals e to the 10th power? That's just 10. All right. So now we would actually have to use a calculator for the next ones. And so you should have this feature in your calculator to approximate the value to 4 decimal places. So what I'll do is I will go ahead and share my answers, and then I'm going to also show you how you can check that. Okay, I'm gonna write this in for you. All right, so when I used the calculator, these were the solutions I got, and now in red, I'm going to show you how I would check this. So this would be 10 raised to approximately 2.3010 should give me approximately 200, and then 10 raised to the negative 1.1308 should give me approximately 0.074. Now it will be approximate because we rounded. And then I have e raised to the 5.2983 should give me approximately 200, which checks out. And then e raised to the 0.0050 should give me approximately 1.005. All right, so that's how I would check those answers. All right, we're now going to shift gears into graphing a logarithmic function, and we'll talk about some more general properties of log functions graphically as well. All right, so one thing we can do to help us graph the log of x base 3 is to rewrite it in exponential form, which would be 3 to the y is equal to x. And then we can plot some values, and we can use values for our y to help us out. So I'm gonna use like 0, 1, 2, 3, negative 1, negative 2, negative 3, and I'll just be plugging them in here to get that result. Okay, so when I do 3, and I'll do this in red, so 3 to the 0 power is equal to 1. So my ordered pair will be 1, 0. And then 3 to the first power is equal to 3. So I'm going to have an ordered pair at 3, 1. And then 3 squared is equal to 9. So remember, I'm just plugging these values in for the y. And so I'm going to have an ordered pair at 9, 2. And then 3 cubed is equal to 27. So 27, 3. And so on. Whew. Now we're going to get some fractions, which, are kind of difficult to graph. So we're going to do our best here. So I have 1/3, negative 1, 1/9, negative 2. All right, so exponential and logarithmic functions are inverses of each other. And so the inverse of this, y equals the log of x base 3, would be basically 3 to the x is equal to y. And I'm going to show you on the next page what that looks like graphically. Because remember those ordered pairs, the x and y's, the y's would become the x's would become the y's, the domain is the range is the domain, and so on. Okay, so I'm going to go ahead and plot this for you. So we have an ordered pair at 1, 0, which is not too bad to graph. I'll try my best here. And then 3, 1, 9, 2, 27, 3. And then when I try to graph these here, that's going to be difficult to graph because they are fractions. Okay, so what I want to show you though is it's just going to get infinitely closer and closer to the y-axis. And so we do have an asymptote there for our log graph. Okay, so we have a vertical asymptote at x equals 0. All right, and then our domain, we might as well talk about the domain and range. So our domain is definitely restricted, right? Because we're not going to get to the left of our graph. So our domain would be from 0 to infinity. And then our range, though, you can see it goes all the way down, and eventually this goes all the way up. And so our range is the set of all real numbers, which we can write as negative infinity to positive infinity. All right, let me show you some general definitions here that might help you. This is like really good information here. So it's just giving you some information. You can see that if we have y equals b to the x, that is the inverse of y equals the log of x base b. Because they're inverses, they are symmetric about the line y equals x, as you can see by the graph. The domain of your exponent becomes the range of the log, and the range becomes the domain, right? We see that with inverses. While this has a horizontal asymptote at y equals 0, the logarithmic graphs have a vertical asymptote. And then it passes through 0, 1. Well, this one passes through 1, 0. Okay, so that's like really fun stuff there. Now we're going to talk about an application problem that you're going to see on your homework. All right, we can use the formula pH is equal to negative log hydrogen ion concentration in order to figure out different pH scales and also the hydrogen ion concentration of a solution. So the variable pH represents the level of acidity or alkalinity of a liquid on the pH scale, and H raised to the plus is the concentration of hydrogen ions in the solution. We can determine the value of the hydrogen ion concentration for the following liquids given their pH values. We can express our answer in scientific notation with 3 significant digits. So we're going to be utilizing this formula to solve these problems. So we're going to start with acid rain, which has a pH of 2.3. And so what I'm going to do is I'm going to rewrite this formula for you. And we're just going to plug the pH in and do a few things here. So the pH is 2.3 for acid rain. And then what I want to do is I want to get the log completely isolated. So I need this log to be isolated. And so I need to get rid of that negative. And to get rid of a negative 1, I can just multiply or divide both sides by a negative 1. And so when I do that, I'm going to end up with the log of the hydrogen ion concentration is equal to negative 2.3. Now, once I get to this point, I want to rewrite this as an exponent. And so to do that, I'm going to remember that the base is 10 because it's not written. So the base is 10. It's the common log. So this would be 10 to the negative 2.3 is equal to the hydrogen ion concentration. All right, now this is asking me though for the scientific notation. So I at this point, I would want to use my calculator to type this in and to convert it to scientific notation. And if your mode is in scientific notation, it will do that for you. And everybody has different calculators. I'm not sure which calculator you're using. But if you do this correctly, you should get about 5.012 times 10 to the negative third power. So the concentration of hydrogen ions in acid rain is 5.012 times 10 to the negative third moles per liter. All right, So let's try this next one, which is milk. So milk is 6.2. Now you can imagine when I plug in 6.2, I'm going to have the same operations, right? And so I want to just point out that it is helpful. So when you're given the pH, it is helpful to use the formula converted into the hydrogen ion concentration, which would basically be equal to 10 raised to the negative pH power. All right, so this is going to be 10 to the negative 6.2 power for milk. And then I can use my calculator and I'll end up with 6.310 times 10 to the negative 7 power. All right, I hope this video helps and I hope you have a great day. Bye.